No, I mean, Spanish would be a disaster.
Except for Spanish.
Chinese would be equally bad.
Okay, Chinese and Spanish.
I don't know. I'm trying to think. Well, like, part of it is like any of these other courses are kind of like introductory anyways.
Yeah.
Because you should physics.
Yeah, like chem would be easy. Well, I mean, it was my undergrad, right? Like, I know it. And, you know, I've taught physics before, not at this school, but at another one.
You should teach
AP physics. I don't like physics.
Me either.
You know what, as a mathematician, what bothers me about physics is that, especially the way that we teach these non-calc based physics, is we go out of our way to, like, we do like these weird tricks for specific, like a really specific trick for a really specific situation, rather than just dealing with some like kind of gross math. I'd rather just deal with the gross math and do it the same way every time than like have these million little tricks to avoid having to like, oh, you have to use sine or cosine in this problem, so let's just like do this thing to work around having to do sine or cosines. It's like, I'm okay just thinking about these as vectors and just doing like vector algebra here. Like, that's fine. I'd prefer to do it this way. And we do a lot. It seems like you do a lot of that. You know, like when we did in trig, where you do like the box falling down the ramp.
Yeah.
Oh my
Like,
God.
those problems are so annoying in physics, because like every situation, it's going to be like, we're just going to be twisting stuff all the time. We're going to tilt the axis and like do all this. It's like,
flipped and it's weird to use sine and cosine.
yeah,
It's weird.
but like the way you do it,
But like I was doing it like the same time.
yeah, you do it in the way we do it in trig, and every problem is identical.
Yeah.
And it's like, oh, I'd much rather do it that way.
I should have done that rather than learning two different ways.
Yeah. Anyways, let's pick up where we left off here. Did I? Oh man, what happened here? Did I do? Okay, so we did these things already. Good. Okay.
Apparently.
Oops. That's not what I want to do. Where did that fish go to? Oh, there we go. Sorry. All right. So we did this all last time with the absolute value stuff, right?
Yeah.
Okay. We didn't get that far in second hour. I just want to make sure that, like, I see this in here. I'm like, this isn't what I did during second hour, was it? No, it wasn't. Okay. All right. So we have these last two theorems here to talk about, and and an example to run through. So theorem 2, it just says if we have a function f of x that's always less than or equal to g of x, as long as you're near some number a. So just like in a specific neighborhood, if f of x is always bounded above by g of x, then not surprisingly, the limit as x approaches a of f of x has to be bounded above by the limit as x approaches a of g of x. So basically what it's saying is, like, if you have a situation like this is f and this is g, no matter where you pick your a at, say like a is here, the limit of f of x will always be less than the limit of g of x, which is exactly what we're saying, right? That's kind of the idea. Is everybody okay with that idea? So that's nice, right? Is what we've done is we've created like a situation where we can upper bound or lower bound the limit for a function. If we take those ideas together, the idea of an upper bound and a lower bound together, we get something that's called the squeeze theorem. Now, this is one that's important. This is one that you'll want to have memorized. This will be something that I think almost every old AP exam I look at in the free response, there's some kind of question that runs into like squeeze theorem. Probably there will be, like a multiple choice question that's like the way to do it is just using the squeeze theorem. Thanks. So this is one that we want to make sure that we're comfortable with, because it's rather specific, and I'm thinking that it would likely show up on an AP exam for you. So what the squeeze theorem says is if I have some function g of x and a function f of x that's a lower bound for g of x and a function h of x that's an upper bound for g of x, and that's true not necessarily for all values of x, but as long as x is near some number, right? As long as there's some little section of it where this is true, then the limit as x approaches a, that's a number where it's true, of f of and the limit for the lower bound is the same as the limit for the upper bound, then the limit of that function in the middle is also the same thing. So what we're saying is, like, say we have like an upper bounding function, a lower bounding function, and then here's like our g of x, and like our value for a is like right here. If the limit of the upper bound is the same as the limit of the lower bound, we know that like whatever this limit has to be bigger than the limit for g of x, and the limit for the lower bound the limit for the upper bound has to be less than or equal to the limit for g of x, and the limit for the lower bound has to be greater than or equal to the limit for g of x, and they're the same number. It means that g of x just has to be that same number, right? At that point there, that limit value has to be the same for all three of them. That's what we're saying. Chanel?
Wait, so I'm just confused. What do you mean by like H? Like, which one is greater than which one? I'm just confused about that one.
Sure. So, sorry. This guy would be like our h of x, because it's bigger than or equal to all the values in A, or in the red one and the light blue one.
Okay.
This guy would be like our f of x, because it's less than or equal to all the values in the light blue one. And this is like our g of x.
It's like in the middle.
Like in the middle of them.
Okay.
So what we're saying is if the green is our point A that we're taking the limit to, if this limit of the upper bound is the same value as this limit for the lower bound, the thing in the middle also has to go to the same limit, right? That's what we're saying. Does that feel good?
Yes, thank you.
Okay. So let's look at an example. So this one, example number 11, is like the worst case scenario for a squeeze theorem kind of problem. In most of the situations, what you'll get is you'll get a function for f of x, the lower bound, and you'll get a function for g of x, the upper bound, and you'll just be asked to find the limit as the middle thing approaches some number. And just the way you do that is just by taking the limit of the upper and the lower bound, and if they're the same, that's the answer. If they're different, then you can't tell. But the problem we're going to look at, we haven't supplied you with a function that's a lower bound, and we haven't supplied you with a function for the upper bound. What we're going to need to do is find those ourselves. So let's first observe why we would need to use the squeeze theorem in the first place. Okay? What would happen if, first of all, can I do direct substitution on this? No. Why not?
It's going to be undefined.
Being 1 over 0 sine.
Nope. I can only...
It's not a rational or polynomial.
There you go. So that function is not a rational function or a polynomial function, so I can't do direct substitution on this. Now, you could use... Let's see, where's the... Is it in here or is it not? Okay, not in this section. That's okay. All right. So we can't do direct substitution, but even if we could, you'd have 0 times sine of undefined, which, like, what the heck does that mean? that looks a lot like 0 times infinity to me, which is one of those indeterminate ones anyways, right? So there must be a different way of doing this. The different way of doing this is going to be using the squeeze theorem. Let's move that out of the way. I said to move you out of the way. Okay. All right. So what I need to do is I need to come up with a value for f of x. That's my lower bound. And I'm going to treat g of x as this thing we're looking for the limit of. And then I need to come up with something for h of x. That will be an upper bound.
How do you tell that, like, this one is going to be g of x instead of f of x or h of x?
Well, because here's the with the squeeze theorem, g of x is what you're going to find the limit of,
Oh, got it.
right? Because that's the thing that's hard. So what I'm going to do is I'm going to find something that sandwiches it,
Okay.
that are easy to find the limits of, and as long as they have the same limit, then I know the answer for the middle,
Okay.
right? Is that okay?
Yeah.
Okay. So my goal now is I need to figure out a function f of x that's a lower bound for g of x and is also easy to take the limit of. So when I look at this, I see the product of two functions. When I look at g of x, I see the product of two functions. I see x squared times sine of 1 over x. Everybody agree? Okay. So, if I think about x squared as a function, is x squared bounded? Is that a bounded function? Great. What does bounded mean? That's a great question to ask, because if you don't know what that means, how are you possibly able to answer? What does the graph of x squared look like?
It's just like
It's just a parabola, right? So we would say that x squared has a lower bound, because you could pick like y equals 0, which is less than or equal to all values in y equals x squared, right? Everybody agree with that? But does it have an upper bound? No. So I would say that's unbounded, right? Because there's going above. Now, okay. If you're not, stop me. We can talk more, okay? That goes for everybody though, right? If you don't understand, stop me. We can talk more. So now let's look at sine of 1 over x. Now this looks confusing, right? What the heck does sine of 1 over x look like? Here's the thing. The 1 over x part doesn't matter. I can just think of it as sine of x. Because when we take the sine of something, it doesn't matter what that something is, right? We know we know sine of something is gonna look like, right?
Yeah.
What's the graph of sine of something look like? Yeah, right, looks like this or something. Well, oops. You know, like that, right? Everybody agree? Is this bounded? Yes, right? What's it bounded by?
Why do you think minus 1? We bounded means like sandwich by 2 lines.
Yeah, is there a number that's, in the upper bound sense, is there a number greater than or equal to all values in the function? Or in the lower bound, is there a value that's less than or equal to all the points of the function? Okay. Everybody agree with this? That's going to be my key. So my lower bound, my f of x, instead of using sine of 1 over x, what if I just replace that part by -1? Because whatever sine of x is going to be, or sine of 1 over x in this case is going to be, I know that -1 is less than or equal to it, right? And for my upper bound, what if I replace the sign of 1 over x by positive 1? Because I know positive 1 is going to be greater than or equal to anything that sine of 1 over x could output. So let's just look in our calculator and see, does this indeed sandwich our function g of x, right? So if I do negative x squared times sine 1 over x, and then x squared. So there's negative x squared. Here's x squared sine 1 over x, and there's positive x squared, right? Like, looks like it sandwiches it to me. You guys agree?
Yeah.
Okay. So what I can do then is I can look at the limits for f of x as it approaches 0. How do I do the limit as x approaches 0 of x squared? No, man. No, man. Direct substitution, because this is a polynomial. So it's just 0, right? Then we'll do the same thing for our h of x, which again, direct substitution is just 0. What can I say now? Since those are equal, the limit as x approaches 0 of our g of x also has to be 0. Oops, we should say, actually, let's do it this way. We should do it this way, because it says show, right? So I should provide a little bit more justification. I can say then, by the squeeze theorem, the limit as x approaches 0 of g of x equals 0. And now I'm done. So this part was really the hard part, right? Doing the limit of f of x was trivial, right? And doing the limit of h of x was trivial. But because I was careful and set up my inequality, those two limits then give me the limit of the thing that I couldn't do with a substitution. Do we feel okay on what we did here with the squeeze theorem? Bless you. If you looked at the homeworks, come on. So like 36 through 40 are all squeeze theorem problems. I can't remember what I assigned. 37 was one of them. Okay. Notice for like 37, this is the easy scenario, right? Where I've given you the lower bound and the upper bound and just asked you to figure out the limit of the thing in the middle. How do we do this? I take the limit of the left side and the limit of the right side, and if they're the same number, that's the limit for the middle. If they're different numbers, then you can't do it. What's the lovely part about doing the limit of the left side and the right side? They're polynomials, so I can just do direct substitution on them. So it's whatever. 16 minus 9, that's 7. 16 minus 16 plus 7 is 7. So the limit of f of x is 7. Done. By the squeeze theorem. You should state that you use the squeeze theorem. Yeah.
But then like a harder problem would be if you're just given the f of x.
Like 39. Yeah, where this is our g of x. That's our thing in the middle. Right? So you'd have to find a upper bound and lower bound here.
Is cosine, is that also negative 1 and 1?
Yeah, that's exactly right. Cosine would also be bounded by negative 1 and 1, so you could use the same trick. At this level, if we're asking you to find the upper and lower bounds, there's probably a trig thing in there that's going to make it give you the bound that you need. Should be relatively straightforward in that case. Can I zoom in?
Yeah.
Yep, so you'll replace the sign with like a negative 1 or a positive 1, respectively. You have to be a little bit careful there.
Wait, so for 40, like, you cannot use, I don't think you can use that negative 1, 1 trick, right? The one that we used for the nodes. You can't use that trick.
Well, you have to be, here it's a little less, no, I think it's going to be fine. It's just 1 won't be negative and positive, but you'll just have e to the negative 1, e to the first. That's just a constant,
Okay.
right?
So you would just make it like sine of x, like we did, like in the example, like pretend it's
I would pretend like it's sine of x, yeah, because it doesn't matter what's inside of it. Sine of something is always going to be between negative 1 and positive 1. It might, like this one, it might have an undefined spot, like where it's, where x is 0, but that doesn't matter. Like a single discontinuity isn't going to cause us any problem here doing the squeeze theorem, because we don't have to have the inequality holding at all values. It just has to be the area around A, and the A in this case is 0, which is where we have the undefined part, so the undefined part is fine. It's okay?
Yeah.
Sure. So that's the idea for the squeeze theorem. Do you guys want to talk about homework questions from 2-3? You guys got any of those? Probably a couple. 8, 24, 23. Give me some lines here. Okay. Yeah, Chanel?
Number 10.
10? Oh, this one, everybody, they asked about this in second hour too.
Oh, okay. I'm glad I'm not the only one.
Yeah. It's like way easier than you think. Okay. What's wrong with the first line? Did anybody catch what was the matter with this? Brooke?
If you plug in 2 for x, it's going to be like 5 and 11.
And on the right, it would be 5. So we should include that.
So I have the reasoning right.
Okay, good. So that's what's wrong, is that for those two things to be equal, you can't include the next value of negative or of positive 2. And then this is now exactly, what is it? It's this theorem, right? Where f of x is the rational and g of x is the linear and a is 2, right? It's exactly this theorem. So that's still true, even though those things are equal everywhere except at a given point. Their limit, even at that point, is going to be equal by this theorem.
So you can use, wait, so I'm confused. So you can use 2, like you can plug in 2 here and like find the limit?
Well, you're not going to be able to do direct substitution at 2
Okay,
on the left because you'd get 0 over 0.
okay,
But you can do it on the right.
okay.
and you get 5, which is also going to be the limit for the
Oh,
left.
I got it.
Because we know the limits are equal.
Okay, yeah.
And we can do direct substitution on one, but not the other, which is great, because I like doing direct substitution because it's really easy,
Okay,
right?
thank you.
Yeah, no problem. Katie, did I see your hand also?
Yes, can you do number 32, please?
Sure. Oh, this one just looks nasty. All right, let's see here. So, first things first, if you try to direct substitution, you change your h's into 0, you end up with 0 over 0, which tells you, okay, can't do that. What I would probably do first is I would start by making a common denominator in the numerator of this. What would that common denominator be?
X squared.
Great. X squared times x plus h squared. So the first fraction we'd have to multiply by x squared over x squared. And the second fraction we'd have to multiply by x plus h squared over x plus h squared. So far, so good. And here, I'm probably going to do two things. So that's an h. In this same step. One, I'm going to think about like multiplying by the reciprocal, just to get this down to a single fraction. So like I'm multiplying this fraction by 1 over h. Okay with that, Katie?
Wait, yeah.
So I'm just doing like multiplying by the reciprocal to kind of clear some fractions up. And then I'm going to FOIL out that other one. I have to be a little bit careful there with our negative sign. That negative sign has to distribute through that entire quantity now. But when I do that, oops, the x squareds cancel. And if I factor off an h from the numerator, shoot, forgot my limit. Oh, just FYI here, guys, this is a nice opportunity to point this out. Notice how after every equal sign, I'm rewriting the limit as h approaches 0. On a problem like that, if you do not do that, the AP grader will not give you credit for this problem. They will mark it wrong. You'll get no marks for it. You can only dump that limit once you've done a direct substitution or something else to eliminate the limit symbol. As you're doing these algebraic manipulations, that limit has to come with you. You cannot just stop writing it after the first step. It has to come with you every step. Okay? Just as a heads up. I'll be looking for it in your homework and I'll make comments about it. It'll matter on your tests and stuff. I'll make comments about it. Okay? So be conscious of that. So here I can reduce. After I do that, what's going to happen if I do direct substitution now? It's good, right? So I end up with negative 2x over x to the 4th, or negative 2 over x cubed. Notice now when I did the direct substitution, I dumped the limits because in doing the direct substitution, the limit was now evaluated. It's gone now, right? Going from this step to this step where I did the direct substitution, the limit symbol is now gone. Everybody's good? With when to hang on to it, when to dump it?
So just make sure you would dump it because you're technically already like evaluating it, you're already like taking into account.
And now there's some reducing for me to clean up at the end, but like the limit is now finished.
Okay.
And as far as like an AP grader on a free response question, they should accept this, even if it's not simplified. Now, if it's a multiple choice question, you'd have to like realize that that's the same thing as where I ended up at. But if it's a free response question, they are not going to be grading you on simplification. Okay? Unless it says specifically like show this thing is equal to that thing. But if it's just a problem like do this limit, if you got to the part that I circled in green where the limit's been evaluated, even though you haven't simplified, they should still take that as a final answer. Okay? As we kind of continue to go, we'll talk more and more about like what the AP would be looking for, like what's a good enough answer, because some of these coming, in the future, the worst part can be the cleanup at the end to get the answer in the back of the book where it's like, well, that was like longer than the problem was to clean it up to get to the answer in the back of the book. So like that's not always necessary, right? All right. Katie, this was yours, right?
Yes.
And you feel good?
Yeah.
Okay. Did you make the correct first step in trying to make a common denominator
I
there?
think I did it all with copies of the class.
Oh, you did at some point the h approaches 0 turned into x approaches 0 or something?
Yeah.
That's an easy mistake to make. But good. Again, the key would be realizing what to do first. If you can't see that, like, okay, better make a common denominator in the numerator and start kind of grinding this down, looking for something to cancel, you're not going to get anywhere, right? Like, at some point, that has to happen. Nolan.
25.
Sure. Yeah. Okay. 29. Again, if I try to direct substitute this thing, I get like 1 over 0 minus 1 over 0, which feels like that's not something I can really count on evaluating. So what I would probably do here first is I notice that there's a greatest common factor, that both of these terms contain a 1 over t. So I would probably start by doing that. That feels like that'll make the algebra a little neater along the way. Oops, that's a minus sign in between them though, Kulik. And now I'm just going to make a common denominator. Actually, I'm going to not write that one in quite yet. So here, I've gone ahead and made a common denominator, but nothing's canceled out, right? But if I look at that numerator, that should be screaming to me to do the conjugate. Do you agree? Okay. If I'm losing you or you're not sure why I did something or you have a question, please interrupt. You guys are welcome to do that. I'm going to FOIL this out just kind of in my head. Is everybody okay with me doing that? Okay. If you weren't, you're obligated to be like, yo, Mr. Kulik, I didn't see, what did you just do? That's looking pretty gross, but good things are about to happen here. So if I distribute that negative through the numerator, I'd have that, right? So those guys will cancel. And then those guys can cancel. And I'm left with like -1 over.
Oh,
Because of the t was negative. Yep. I heard the whispering. You nailed it dead on. And now I have something that I can just kind of direct substitute, right? Now, note that this is not, these are radical functions, but I can use my limit laws to just like push the limit underneath both of these radicals and then direct substitute. So I'm just going to direct substitute it. I realize that I'm doing some other limit laws also in doing that, but like it's okay. You're okay with that, Nolan?
Yeah.
Okay. So I get 1 over 1 times 2 or 1/2. And that should be where we end at.
I think for that, is it factor out the lower t at the beginning? It's got really messy.
Yeah.
And like tell what's going on.
Right, like it can, yeah. So again, like did you need to multiply or FOIL out the t or factor out the t in the beginning? No, it's still, you can get there. I think it's going to get, it probably got pretty messy when you started doing common denominators and trying to simplify stuff. And then seeing the conjugate for it, yeah, it was probably rough because you probably had radicals in both chunks or something,
Yeah.
which is tougher to see what to do with that. But it still could have been doable. It just would have been less obvious maybe what to do. But not wrong. Sure. Some of these, like, you guys starting to appreciate when I said, like, the first day of class that the common experience is the calculus part is the easy part. It's the algebra that's hard. You're starting to be like, oh, yeah, the algebra here gets pretty nasty. All right. So what I would probably do here as my first step is to get rid of these negative exponents by just rewriting these as reciprocals. Okay with that? Okay.
Oh, yeah.
Now I'm going to make a common denominator, which would just be 3 times 3 plus h. So in the numerator, I'm going to have 3 minus 3 plus h over 3 times 3 plus h. And I'm going to do like the 1 over h and do that also at the same time. Is that okay? So when I distribute that negative through, I have that. So those guys can cancel, and the h's can cancel. And hopefully you're seeing that, boy, Mr. Kulik, this one reminds me a heck of a lot of that first one of these that we did. So from here, we can direct substitute. I think we just end up with negative 1/6. It was just a little, I used less steps than I did, but it was basically the same problem as number 32, right? It just was less yucky because instead of having squareds here, they were just to the first. You just had to recognize that, like, hey, if I just write these as reciprocals, it's the same kind of problem.
Why did you put H over 1?
So that I multiplied by the reciprocal, that's how I got it down there. Right? That's all. That's why I wrote it as H over 1, was just to illustrate, like, okay, and then I multiplied by the reciprocal, so like whatever fraction I made here, I just stuck the H in the denominator. So I did two things in one step there instead of just like one thing. But since it was like the same kind of idea as the previous one, I felt like that was going to be okay. Okay. So on these limit ones where you're getting like an indeterminate, the things that we want to try, right? Factor and reduce, multiply by conjugate, make a common denominator, and then look for stuff to cancel, right? There's going to be some way to do it. We just have to like grind through enough algebra until we cancel out the parts that are the problem. Anybody else? Yeah.
Could you do 25?
Yeah, this one was a nice one. All right, so we look at this, and what's the first idea here? Yeah, I would just start by multiplying by the conjugate. So when I FOIL this out, I'm just going to go straight to the FOILed out, right? Everybody's okay? So I'm going to have 1 plus t minus 1 minus t over t times square root 1 plus t plus square root 1 minus t. Now I'm going to distribute the negative in the numerator. When I do that, I just end up with 2t. Everybody's okay with that? Can reduce the t's. Oh dear. And now, if I direct substitute, again, I recognize there's radicals here, but like as we discussed previously, like there's a limit law that would allow me to push the limit under the radical, and then I can just direct substitute because it's a polynomial, so it's all okay. It looks so easy when you do it, Mr. Kulik. I know. Think of it this way, though. This, I think, is year 16 of being a math teacher. So imagine you're doing the same math classes over and over and over again for 16 years. Like, how good would you look at doing this kind of work? You'd look really stinking good at it, right? I was just as big, and I made just as big a mess out of these problems when I was doing it the first time as you did. This is my 16th year doing this kind of stuff. That's why it looks so easy. Don't be frustrated if it's like I made a mess out of this. You did it so quickly. That's what's going on. I see exactly what to do because I've done literally like thousands of these kinds of problems. It's just practice. I'm no smarter than you are. It's just been like developed more because I've had way more practice. Nolan.
For number 13, so I got the answer of undefined, but I ended up just like looking at the individual limits as it approaches 5 on both sides. Is there like a better way to find out if it's or if it doesn't exist?
Okay. For this one, no, because if I do the direct substitution, we end up with 6 over 0. That's not indeterminate, right? And if I try to factor this thing and reduce, nothing reduces, right? It's set up to make it look like it's going to reduce, but it doesn't. So yeah, literally, if you look at the limit as x approaches 5 from the left, the bottom, I'm just going to write this as f of x here. I don't want to rewrite that thing. The denominator is going to be negative, right? Because you have something a little less than 5 minus 5. The numerator is still going to be basically 6. So this is going to be like, this is like negative tiny number, right? So if I divide by a tiny number, what's happening to the numerator? It gets huge, right? If I take 1 and divide it by a half, I get 2. If I take 1 and divide it by a fourth, 0.25, I get 4. If I divide by an eighth, 0.18, I get 8. The smaller that denominator gets, the bigger the result. When I divide by a negative, or divide by a decimal, everybody's okay? So this is just like bombing off to negative infinity. If I do the other way, again, the numerator still is basically 6, but this denominator now is going to be a positive tiny result. So that's going to positive infinity then. And because these are disagreeing, the limit doesn't exist. That's kind of the idea. But no, there's not a good algebraic way of doing it short of kind of what I've kind of talked through there. Eventually, like in another chapter or section or two, yeah, so like when we get to 2.6 or whatever, we're going to start accepting these kind of things and not saying the limit doesn't exist. Well, the limit doesn't exist here because they disagree. But if they're both infinities, we'd write just infinity eventually. I can't remember where the textbook is at right this second, but that's the idea. So that was a good question on that one, Nolan. Katie.
Do you just test both sides if you can't factor it or plug?
Sometimes. And this is the frustrating part about this course, is that you're looking for like every time thing, and limits aren't like that, unfortunately. Limits are like, okay, if it's indeterminate, there's some stuff we can try, right? And we're going to get more tools for indeterminate cases when we get further in, because the tools we're using right now are not the best tools, but we don't have the other stuff we need to do it a better way. But if you have something like that where you get 0 over 6, when we plug it in, the tempting thing is to just call that infinity, but it's not. You have to worry about like what each end is doing, so like that's what I was doing here. It just kind of depends a little bit, Katie. I know that's a crappy answer, but okay. So I said also, so we're not going to go forward any today, but what I do have for you guys to work on for next time is I made a little multiple choice practice for you guys on the MyAP. Now, the site's going to grade this automatically for you and tell you like what your grade is and what how many you got right and wrong or whatever. I don't care about that. Like, I just want you to do it and for us to talk about. So, like, don't get bent out of shape about, like, how many right and wrong you get. Just try to do the best you can. And I'm not going to count it as anything other than, like, a participation thing. Okay? So don't, like, it's the first time doing something like this. So the thing that I assigned here is called Chapter 1, Practice Number 1. All the questions I picked are things you should be able to do with no calculator. At worst, you have whole number, multiplications, additions, subtractions, which I think we can all handle without a calculator. Try to do it with no calculator as a practice. There's just 11 questions. You can take as much. Oh.
High school students, we're attempting to pray to end our day together. So let's stop for a moment, let's quiet our minds, and let's open our hearts as we end this day.
I'll talk for just one more minute after this.
And the Holy
You guys can hang for a minute.
Please join me in a Hail Mary. Hail Mary, full of grace, the Lord is with you. Blessed are you among women, and blessed is the fruit of your womb, Jesus. Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death. Amen. Notre Dame, speak of wisdom, pray for us. In the name of the Father, and the Son, and the Holy Spirit. Amen.
Just hang for one.
Afternoon, Notre Dame. God bless. Teachers, may this and you are ready.
So again, try to do this for next class. We'll talk about this at the start of class. We won't have any homework quiz, but try to do this. Okay? Try not to use a calculator. You can take as much time as you want. You can talk to anybody you want. You can look things up if you want. The point is to just kind of start getting used to doing things with no calculator, taking multiple choice questions. We have, I think, 2 more sections of real notes before I'm planning on a test. I will have some multiple choice questions on the test to kind of get used to this kind of format. So just take this as practice. Nothing more than that. Don't worry about the grade on it. We'll go through the right and wrong answers and talk about how to do them next time. Okay? See ya Monday.
What do you plan the first week to be around?
It probably won't be next week, be the week after.
Next week or week after?
Not next week.
Oh, week after?
Yeah, probably not the week after. I mean, I still have 2 sections to do. There's only 3 class days next week. There's no way I'm going to cram a test down your throat. Oh, there's only 2 class days next week because there's only 4 days of school.
Okay.
So couldn't even have a test next week if we wanted to. Probably sometime the week after.
Alright, got it.
Yeah, if I was
You're welcome.
on the roster, I was
Cool.
What do you have GitHub for?
What's up?
What do you have GitHub for?
For my coding stuff, so I can like,
Sync it up.
yeah,
I have a syllabus for,
Oh.
was it 8th hour, 4th hour? I don't know.
4th hour.
Yeah.
No, 8th hour. Today's 4th hour.
I used to do a ton of coding, so I thought that was cool.
Yeah. So like, part of my dissertation for my graduate degree, I wrote a big solver for this specific type of problem.
Really?
So it's like, I don't know, it's a couple hundred lines of code or whatever. But managing that, like going back and forth between my advisor and stuff,
Yeah.
like that was the easiest way to kind of share
Oh, for
that
sure.
and update, you know. Because there's times where you make an update and it's like, oh, that didn't work at all.
Yeah.
Okay, can we recover this back
No,
to?
it's helpful.
Yeah,
I had it on my school laptop for a while.
Yeah, but I think with you guys, I think it was an issue, right?
Yeah.
Wasn't it? They don't like
They don't like it now.
the sharing properties of it or whatever.
I don't know.
But yeah, I think it's like quite helpful
Yeah.
in terms of like managing versions of a program or whatever, so you can like
Yeah.
make some changes, test it out, decide if you want to keep it or not.
I used to do a bunch of freelance work, like software development and stuff.
Okay.
I had like a little company I started, and then this guy tried to recruit me. Someone in Colorado, and I was like, I'm 15. So he was like, okay.
That's funny.
But yeah, so I just thought that was cool.
Yeah.
Like I used Visual Studio Code and all that stuff. Like
Okay.
an external server.
Okay. Yeah, I mean, I do all my work just like in Python or whatever. I've used Visual
Yeah.
Studio to do stuff in Python
Yeah,
before.
syntax,
But yeah, I mean, it's fun. Like
Yeah.
it's just like a cool thought exercise or whatever.
I was self-taught and all that stuff because I like when hearing people say like, "How did you learn how to do that?" Like, It's not actually super
Yeah,
complicated.
it's
or anything.
like once you figure
It's a
out,
puzzle.
well, and it's like so much of it's Googleable.
Yeah.
Like it's just like,
All
okay,
of it.
I want to do this. How do I do that?
Just plug and play.
Yeah, and it's like, oh, you find some Stack Exchange doing the exact
Yeah.
same. And it's like, oh, okay, that's the
Oh,
syntax
yeah.
I need.
A million forms open at once.
Yeah, for sure.
Well, have a good weekend.
Yeah, take care, Ben.
Can I just ask you how I would do this problem
Sure.
from here?
Okay. So what I would do is we can do this, but I don't want to direct substitute this because I have a
Right,
zero
because then you'll end up
denominator.
with 0, yeah.
What I am going to do though is I'm just going to multiply this to the other side like it's a constant.
Okay. Alright.
Now I can do that.
You're
That
just
just
gonna-
becomes 0.
Yeah.
And this,
Wait, it becomes 0. Oh, yeah, because it's 10 times 0. Okay.
Yep. then we can write it as that. And I can do this,
Mm-hmm.
and that's just 8. So I
Right.
add the 8 over.
That's it.
That's what I'm looking for, right?
Oh, okay. Alright.
It was like,
Not nearly as bad as I thought.
no, but it's one of those things like, would I have thought of that?
Right, yeah. No,
Yeah,
I'm like,
Until I see it as something like a trick I can do, I'm like, that makes all the sense in the world.
yeah, right.
How I don't think I would have come up with that. And it's like, that's okay. You're not necessarily supposed
That's
to.
where I was going to come and ask you. 'cause I was like,
Yeah.
Alright, thank you.
You're
Have a good
welcome.
weekend.
You too. All right, let's get this in, and then I can sit down and try to. Bloop. Relax. Indoors. Oh.